All right, so now we are ready to do some example problems for the chi-square test for goodness of fit and the chi-square test for independence. So in this first example, we are looking to see if there is a significant difference in the proportion of accident havers based on age. So we're really wanting to see if the high cost for insurance for younger drivers is justified, thinking that younger drivers are in more accidents. So we look at 300 accident reports and we group those accident reports based on the age of the driver. Younger than 20, age 20 to 29, and 30 or older. So in step one, the hypothesis for this, so for the null, the distribution of accidents is not significantly different across age groups. The distribution of what we're measuring, number of accidents, right, number of accident havers, is not significantly different across age groups, the different groups. And then the alternative, the distribution of accidents is significantly different across age groups. Now for step two, we need to find, so step two, we need to find chi-square crit. And chi-square crit is based on the fact that we know our alpha level is 0.05. So alpha is 0.05. And our degrees of freedom, which for the chi-square test for goodness of fit, degrees of freedom is equal to the number of columns minus 1. We have 3 groups or 3 columns. 3 minus 1 is 2. So if we go to the table for the chi-square distribution, we find 0.05, degrees of freedom 2, 5.99 is our critical value. So if we drew our chi-square distribution, it would look like this. Remember, it's a positive skew. 1 is right here. And then 5.99 represents the cutoff or the start of this rejection region or the critical region. So if we have a chi-square that we calculate in step 3 that's 5.99 or above, we can reject the null hypothesis and conclude that the distribution of accidents is significantly different across age groups. So now let's do our calculations to find out if we can in fact reject the null hypothesis. And let's do those over here. All right. So for this one, we need to figure out, before we can start doing the chi-square calculation, which looks like, well, I'll write it down later. Well, let's write it down now. So the formula for chi-square is equal to the sum of the observed frequencies for each group minus the expected frequencies squared divided by the expected frequencies. So we have our observed frequencies right here. These are our FOs, observed frequencies in our data, but we need to find the expected frequencies. And the expected frequency is dictated by the null hypothesis, which states that the age-based proportions for the number of accidents is equal in each category. So the proportion of registered drivers in each category, or the proportion expected, remember that is equal to 1 divided by C, or 1 divided by 3, which would be 0.333. So if we're using that FE formula that looks like this, the proportion expected multiplied by n, then we would just say 0.333 multiplied by, well, what is our sample size? So n equals, so 68 plus 92 plus 140 gives us 300. You also know it's 300 because I told you right here, 300 accident reports. And 0.333 times 300 gives you 99.9. It is okay, even though we're using frequency-based data, which is a discrete type of variable, it's okay to have decimals for your expected frequencies. Now you'll see that when you use the different methods for coming up with the frequencies expected, there's a little bit of rounding error involved, so you may see slight differences. So for example, if we use the easier formula for frequency expected, which we can use when we have a chi-square test for goodness of fit and our null hypothesis is stating that there's not a significant difference across groups and it's not based on any kind of proportions in the population, we can just do n divided by c. So 300 is our sample size. We have 3 columns or 3 groups, and 100 is the expected frequency. Now, remember, there's a little bit of rounding error going on, and we're pretty much saying when we look at this that 33.3%, if we turn this into a percent, of the sample of accident havers would need to, if the null hypothesis is true, then 33.3% of accident havers would be younger than 20. And 33.3% of accident havers would be between 20 and 29, and 33.3% of accident havers would be 30 years old or older, if the null hypothesis is true. Or in other words, we would have equal frequencies for each group if the null hypothesis was true. So if we draw out our expected frequencies, and I encourage you when you do your expected frequencies to mimic the frequency observed table, and you'll see why that makes your calculations much simpler once we get to the point where we're using this formula right here. So FE table. So we've got younger than 20, 20 to 29, and 30 plus. And for each group, we're expecting, if the null hypothesis is true, to have 100 in each group. All right, so now let's go ahead and do our chi-square calculation. So chi-square, and remember our formula up here. So for the first group, and actually these are all going to have the same FO, right? Or sorry, the same FE. So the first group, the observed frequency was 68. The expected frequency was 100. Square that. And the expected frequency is 100. And I'm putting a plus here because remember, we're summing all these up for each group. All right, the next group, we observed 92. Expected was 100. Next group, we observed 140. We expect 100. So 68 minus 100 gives you negative 32. Keep your little square here. I'm just going to do one step at a time. I'm going to solve for what's in the parentheses first. 92 minus 100 gives you negative 8. And 140 minus 100 gives you 40. So negative 32 squared gives you 1,024. Negative 8 squared gives you 64. And 40 squared gives you 1,600. So now I'm going to solve for my division. So I end up with 10.24. 1,024 divided by 100, plus 64 divided by 100, 0.64, plus 1,600 or 1,600 divided by 100, 16. So if we add those together, we get 26.88 for our chi-square statistic. That's huge. That's telling me that my observed frequencies don't quite match up with my expected frequencies under the null hypothesis, which you can see that by comparing the two. And not only do they not match up, but they are significantly different because my 26.88 is like, whoa, it's way off the charts here. So for step 4, so we did step 3 over here. Step 4, we would reject the null hypothesis And we would conclude that the distribution of accidents is significantly different across age groups. So think about what is wrong with this example. There's a reason why this may not be the best course of action for your chi-square test for goodness of fit. So it's really not accurate to assume that the proportion of drivers is equal across age groups. So comparing the frequency of accidents by age to an inaccurate frequency of drivers by age, you're assuming that there's the same number of drivers for each age group. Now think about that. There's probably more drivers who are 30 years old or older. So of course, more accident havers are going to be 30 years old or older, even if they have proportionately fewer accidents than younger drivers. So instead of expecting, under the null hypothesis, expecting equal proportions or frequencies of accident havers across age groups, let's compare the age-based proportion of the accidents, so what you've got here, to the age-based proportion of registered drivers. So we're going to control for the fact that there are more drivers who are 30 or older than there are drivers younger than 30. So now we're doing a hypothesis test examining specific proportions. So we have the same observed frequencies here, but now our expected frequencies are going to be based on the proportion of drivers for each age group in the population. So 16%, or P equals 0.16, of drivers are younger than 20. Between ages 20 and 29, let's make this a little prettier. All right. So between ages 20 and 29, 28% of drivers are in that age range, or P equals 0.28. And then for drivers 30 or older, 56% of drivers are 30 or older, or P equals 0.56. Now pause this video, try to work out the chi-square test for goodness of fit, and I already gave you the alternative and null hypothesis here, based on using the PE times N formula for the frequencies expected, because now you have specific proportions. Okay, so hopefully you paused it and tried that out. Now let's go ahead and go through the answers. So looking at step 1, instead of saying that it was the distribution of accidents is not significantly different across age groups for the null hypothesis, now we're being more specific. The distribution of accidents is not significantly different from the distribution of registered drivers. So we're not just looking across age groups anymore, we're comparing this age-based differences in accident havers to the age-based distribution of actual drivers on the road. And then the alternative is the same as the null, it's just that instead of saying it's not significantly different, we're saying it is significantly different. So now for step 2, we are going to have the exact same chi-square crit, because we still have 3 columns, so degrees of freedom, columns minus 1, is still equal to 2, and our alpha level is still 0.05. So our critical value is still 5.99. All right, let's go to the next page here to do the calculations. Okay, so now we're looking at the percentage of registered drivers in each category. So we're no longer going to have the same exact frequency expected in each one of our groups. So remember, these are our observed frequencies. And we're no longer going to expect the same frequency in each group under the null hypothesis, because under the null hypothesis, 16% of our sample will be younger than 20. 28% of our sample of accident havers will be between 20 and 29, and 56% of our sample of accident havers will be 30 or older. All right, so I'm going to go ahead and just use the FE equals PE times N formula. PE stands for the expected proportion under the null hypothesis, which in this case is based on the proportions in the population of registered drivers. So I'm going to go ahead and recreate this table, and I'm going to say, all right, so we have younger than 20, 20 to 29, and 30 plus. All right. So, for the first group here, we have a PE of 0.16 and our sample size is 300. For the second group, my PE is 0.28 times the sample size of 300. And for the last group, my PE is 0.56 times the sample size of 300. So for my first group, I am expecting, under the null hypothesis, that 48 of my accident havers are younger than 20, 84 of my accident havers are between 20 and 29, and 168 of my accident havers will be 30 or older. All right. So now let's go ahead and calculate the chi-square statistic to see if these are significantly different. So we can already see that they're different, but we need to know if they're significantly different. So let's do chi-square. So the sum of the observed frequency for each group minus the expected frequency for each group squared divided by the expected frequency for each group. So we have 68 minus 48 squared divided by 48. So the expected frequency, the observed frequency in our sample minus the expected frequency for that same group squared divided by the expected frequency. And then we just do the same thing for all the groups. So 92 minus 84 divided by 84, and 140 minus 168 divided by 168. All right, so 68 minus 48 gives us 20. Remember, one step at a time, solving for my parentheses first. 92 minus 84 gives us negative 8. 8. Okay, 8 squared divided by 84. And then 140 minus 168 gives us negative 28. I'm going to square that, divide by 168. All right, so 20 squared is 400. 8 squared is 64. And 28, or negative 28 squared, is 784. All right, 400 divided by 48 is 8.333. 64 divided by 84 is 0.762. And 784 divided by 168 is 4.667. And our chi-square statistic is equal to 13.762. And that 13.762 is larger than our critical value of 5.99. So our conclusion is to reject the null hypothesis and conclude that the distribution of accidents is significantly different from the distribution of registered drivers. Now that's all well and good, and we can see that the chi-square for the hypothesis where we were comparing the age-based distribution of accident havers to the age-based distribution of registered drivers, that chi-square is smaller than when we were assuming equality across groups, because it's a more accurate estimate. It's not as extreme as we thought, right? Because we are basing it, it's like, oh wow, there's a lot of accident havers who are 30 years or older, but now instead of just assuming equality, we're controlling for the fact that we know there are more accident havers who are 30 years, or more drivers who are 30 years older. However, we still haven't really answered the original question, which is asking, is the high cost of insurance for younger drivers justified in that younger drivers are involved in more accidents? Well, originally, if you're looking at this data, it looks like they're involved in less accidents, right? It's like, oh, wow, they shouldn't be paying so much. They make up less of the accident havers. But then when you look at the proportions of drivers based on age, we can tell that we would expect to see them to have fewer accident havers to be that age because there's fewer drivers that are that age. So the question is, now we can look at the observed frequencies, compare them to the expected frequencies based on the percentage of registered drivers in the population, and start to make inferences about what we think is going on. So just like ANOVA, chi-square, if you get a significant result, it really just tells you that there's a significant difference between the observed frequency and expected frequency for at least one pair of groups. But we aren't sure which specific groups have significant differences when we have more than two groups. So I'm not going to have you do a post hoc analysis for chi-square, but I'm going to have you look at the differences between the observed and expected frequencies for each group to infer the differences, to infer what's going on. So we know it's significant, but now we want to know what the answer to our question is. So for example, if we look at the observed frequencies for drivers younger than 20 and between 20 and 29, and compare those to the expected frequencies. So if the proportion of registered drivers was reflected in the proportion of accident havers, we would expect that 48 of the drivers, or the accident havers in our sample, would have been younger than 20, and 84 of the accident havers in our sample would be between 20 and 29. But we actually see that more of the accident havers were younger than 20, so 68 is greater than 48, and more of the accident havers in our sample were between 20 and 29, more than what we would expect, right? 92 is greater than 84. Conversely, if the age-based proportion of registered drivers was reflected in the age-based proportions of accident havers, we would have seen 168 drivers in our accident havers in our sample having an age of 30 or greater. So you can see that, even if really, age doesn't matter when it comes to having accidents, car accidents, we would still expect to see more 30 plus people than 20 to 29 and less than 20, because there's more drivers on the road who are 30 plus. How much would we expect to see? 168. And that's actually less than what we saw in our sample. So in our sample of accident havers, the people who are younger than 30 are overrepresented, and the people who are 30 plus are underrepresented. So I would say that the higher cost of insurance for younger drivers is justified because they represent proportionately more accidents than older drivers.